Hello, I'm Mr. McBrien. This is TIJ1O, circuits, parallel and series. Yesterday we talked about multimeters and we had some tips for using those effectively. Today we're going to fill in sort of the rest of the information that you'll need in order to start building circuits. So we'll talk about resistors in series, series versus parallel, how electrons are lazy, and then we'll cover a bit about converting units. So first off, let's talk about resistors in series. And I'd invite you to, as you're viewing this movie, consider pausing it and thinking about some of these questions as we go. It's useful for you to really think about what you know and what you don't know before we begin investigating things in depth. Okay, so what's a resistor do? What's it actually do in a circuit? Think about that for a second. Well, many of you will have come up with the answer. It slows down the flow of electrons, and that's absolutely true. It slows down current. It resists the flow of electrons through a circuit. Again, true. But another thing that it does is it uses up energy from the electrons as they pass through it. So they begin going through the resistor at a certain level of energy, and when they pass through the other side, their energy level is much lower. So here's a question. What happens if you take an existing circuit and you add another resistor to it? So think about that for a second, please. Okay, and here is our circuit. And if we imagine taking and adding a second resistor to this circuit, we can think about what happens in that case. Now, so here's a cartoon, a schematic for a circuit with 3 resistors in series. And we've even got an arrow in this case showing the direction of current flow. And maybe what you thought about was this idea that when electrons run through one resistor, their energy drops. And you add another resistor, well, their energy will drop even more. And that's absolutely true. And each time they run through these resistors, they slow down a little bit. So each one slows them down a certain amount. If we want to use that old metaphor that I was talking about with talking about resistors as a patch of mud that the electrons have to move through, well, in this case we have 3 patches of mud instead of just one that a hiker might have to walk through. We want to carry that metaphor on. Now, what's useful for us, this is one of the few cases in physics where we get to do something in an additive fashion. Resistors in series add up. So mathematically, the total resistance of our 3 resistors here is R1 plus R2 plus R3. And if we had more, well, they just add together as well. And so we can take and say that the total resistance of this circuit is R1 plus R2 plus R3, and say that about any set of resistors in series. Very easy mathematics. So as an example, we can take this circuit with 3 resistors, one 3 kilo ohm resistor, one 10 kilo ohm resistor, and one 5 kilo ohm resistor, and we can talk about its overall resistance. And it's really very simple. So simple that I'm going to neglect the guess process. Please don't yourself. Oh, no, I didn't. I went and put it in. Good for me. All right, so we're given R1, R2, and R3. Our unknown is the total resistance, or the overall resistance. Our equation, our simple sum of resistors. If we had a fourth one, we could just add that in. Substituting in, we substitute in 3 kiloohms, 10 kiloohms, and 5 kiloohms. And then our solution, 18 kiloohms. Now, we're not done. We haven't asked ourselves the 3 questions. So we can quickly go and verify our units. Yes, the original units were kiloohms. Kiloohms is resistance, and that's what we were asked for. So it looks like our unit's probably good. And if we want to check to see if our answers are reasonable, well, since we added resistors in series, we can expect the resistance to go up. Our number's higher than the highest number here. Things look pretty good. So we can underline that and move on to the next question. Okay, and really, resistors in series are a pretty easy problem to solve, and I'm not going to do a huge pile of examples here. Instead, let's move on to some more interesting cases. Specifically, what happens if electrons have a choice of where to go? Okay, so far we've focused on these simple circuits that only have one path for the electrons. And we've discussed the fact that the electrons that leave the battery have to make it back to the battery. And that means the current has to be the same through every point in the circuit. And there's our simple circuit here. But there's another option. And before we get into that in too much detail, I'd like to talk about the problem, the difficulty with series circuits. So, imagine if every light in your house was on a simple series circuit. Okay, well, your lights could all be quite bright if you designed your series circuit well. It'd look something like this. So the current would flow through each one of the lights. And don't be tempted to make the mistake to say that the current's lower in the third light. Remember, the current's the same all the way through because all the electrons have to pass every point in your circuit. So don't be tempted to make that mistake that some students make. The current's the same through each one of these lights. So they're all equally bright. Billy's room is just as bright as the bathroom. It's all good. So what's the problem with this circuit? So pause the movie if you need to think about it. But what's the issue with wiring up your house this way? Okay, well, hopefully you looked at this circuit and you said, yeah, the issue's pretty clear. If we turn off the light in Billy's room, the bathroom light goes off as well. We can't have independent control of these lights. And that's a serious problem in your house. Otherwise, nobody gets to go to sleep until the last person's done working. Okay, so that's the issue, one of the biggest issues with this design. And we can say, if we're asked, for example, on a test, why series circuits are useful, well, one answer is that we can have one power source and we can have one light on and one light off, independent switches. Another answer is that we can have different current levels. And so here's a parallel circuit right here. You can imagine we could have a switch between 2 and 7. We could have a switch between 3 and 6, and we could have a switch between 4 and 5. And independently, we could turn on or off the current in any one of these. And most real circuits look something like this. They have more than one path for electrons. We call these parallel circuits, and regardless of anything else, if there's a complete line, current will flow through every path. Then it raises a question: how much through each path? Okay, well, we can deal with that, at least conceptually, in this class. So one way we can view circuits is electrons want to get from the negative pole of the battery to the positive pole of the battery. And they will take a given path to get there. But they don't want to do any more work than they have to. right? So they want to take the easiest path they can. And electrons will always do this. We'll always find an easy path if one is available. And more of them will take the easy path than the hard path. It's not a great shock. So in this case, we have a 1.5 ohm resistor on one path, R2, and we have a 3 ohm resistor for R1. And because 1.5 ohms is less than 3 ohms, we get more current going through R2. Now, you might ask yourself, okay, can we say how much? And the answer is yes. And we won't go into sort of the detailed math of this, but I'm going to point something out. Okay, if we look at this circuit, our positive pole of the battery is right here. And this is a conductive wire all the way along. If we measure the potential between this point and this point, it's going to be 2 volts. So we know the potential across this resistor. We also know the potential across this resistor. We can calculate the current between those points knowing those potentials just using Ohm's law. And so we can say a bunch of things here. Certainly we can calculate the current if we want to. We can also say something about ratios. So since R1 has double the resistance of R2, the current will be half as much as through R2. So it'll not just be more going through R2, it'll be double. I guess what I'm saying is we can treat each path as its own independent circuit. And this is why we can turn switches on and off and turn the current off through there. The current through the other resistor, in fact, won't even change. Now, we're not going to spend much time on these in TIJ1O, but we do need to understand one special case, and this is the main reason why we're covering this concept. Let's look at this special parallel circuit. So in this case, we have a 2-volt battery, and we have a load, and we have conductors connecting everything together. So we could easily argue that this is enough to have a working circuit. But there's a problem. So pause the movie, please, have a look at the circuit, and see if you can see what the problem is. Okay, we're back. So the question is, what happens when one path has a resistor and the other path doesn't? And the answer, hopefully you came up with this yourself. We have a normal amount of current through the one portion of the circuit, and the other side is a short circuit. We have infinite current, theoretically infinite current, and our battery will start to heat up and all manner of bad things will occur. And this is a very important lesson for you to learn before you start to build circuits. So, what you need to do, the lesson here, is that every time you build a parallel circuit, you need to make sure that there's an effective load on every one of the possible paths back to the battery. Okay, let's shift gears a little bit, and let's talk about converting units. By way of introduction, I'd like you to think about an idea. How far is it to the north office from here? Make an estimate, please. And humor me and actually try it. Okay, hopefully you've got a number in your head. Now, how far is it to Los Angeles? Hopefully, again, you've got a number in your head. Now, what units did you use for the distance to the office? Probably, chances are, you chose meters. Now, in contrast, when you were estimating how far it is to Los Angeles, maybe you chose miles, but there's a good chance that you chose kilometers, right? So why did you choose that? So by my estimate, it's roughly, say, 60 meters to the office, maybe 70, and roughly 5,000 kilometers to Los Angeles. Now, why did we choose those units? Well, if you think about it for a second, chances are you're going to say, to keep the numbers small. If I reported the distance to Los Angeles in meters, it's about 5,000 kilometers, which is about 5 million meters. And that starts to get to be a very large number. The ranges in electronics are probably even a bit bigger than this. So, as an example, power supply for a laptop will support more than 1 amp, but an LED has a maximum current of about 0.04 amps. Anything more than that, it's liable to blow out. Some of the circuits that we need in grade 11 classes need about 0.000005 amps. And that number is getting small enough, it's hard for me to even judge what that is. Now, in contrast, some of the resistors we have, in my box of tricks that I have at the front of the class, I've got a package of 1 million ohm resistors. So the numbers in our class can get very large and they can get very small. And when we have this kind of large range, we often make the mistake of miscounting zeros. When we miscount zeros, that can be a quite significant mistake. We can be, by definition, if we count the zeros wrong, we're out by a factor of 10 or 100 times. So what we want to do is try to keep numbers in a reasonable range so that we can visually examine them easily, compare them easily, and not make mistakes in counting zeros. And there seems to be a trend throughout the world, regardless of countries, etc., that human beings seem to work well with numbers that range from about 1 to about 1,000. These are just numbers they seem to grasp fairly well. And so what we will tend to do is try to work in that range between 1 and 1,000. And to do that, we have to adjust our units. Now, we could rename every unit, have funny names for units that are scaled differently. And in fact, we do in some cases. We have units like parsecs, for example, that are a derivative of meters, but because the number is so different, we use a whole different term rather than using a very convenient prefix type approach. The prefixes that we'll use in our class, we'll use mega for million, we'll use kilo for thousand, and we'll use milli for thousandth. And that's pretty much most of what we'll use. When we get into the upper grades, we'll use some other prefixes as well, particularly for smaller numbers. And what we'll do is when the numbers are very large, we will convert our units to mega units or kilounits, and when the numbers are very small, we'll convert to milliunits. And by doing that, we should be able to do a pretty good job of keeping numbers between 1 and 1,000. So let's take an example to start. Let's say we were given this question. 3 400 ohm resistors are in series. What's the overall resistance? Now in this case, I really will neglect the guess process. Okay, remember R equals R1 plus R2 plus R3. 400 plus 400 plus 400 is equal to 1,200, and that number is bigger than 1,000. So if we're following our process here, we want to convert this to get it back into the range of between 1 and 1,000. So what we'll do is we'll say, all right, let's convert that to kiloohms. Remember, because the number is too large, we want to use mega or kilo. And I'm not going to give you any tips for how to do that. You'll get a feel for that pretty quickly. Choosing between kilo and mega, that is. Now, there are 1,000 ohms in 1 kilo ohm. That's the definition of that prefix. Or we can also say there's 1 kilo ohm in every 1,000 ohms. This is very important. This part of the process is your key to getting these answers right. Why? Because we can use a little trick. If we want to convert 1,200 ohms to kilo ohms, we can multiply it times this expression. Because remember, another way of using this slash is per. So we can multiply 1,200 ohms times 1 kilo ohm per 1,000 ohms. Now when we take that approach, we can do simple algebra and we can cancel the units to make sure that we're doing this correctly. So ohms is on the bottom, ohms is on the top, they cancel out. Kilo ohms is on the top and it remains there. So 1,200 times 1 divided by 1,000 is equal to 1.2. And kilo ohms is the only unit that isn't canceled. And so we can see that we've got an answer that seems reasonable. Now, but having said that, we can still use our two questions, right? So we can say, okay, we changed from ohms to kilo ohms, so our number should get smaller, and it did. And we also can say every time we use one of these prefixes, it's a matter of 1,000, so the numbers themselves shouldn't change, and they didn't. So this is looking, oh, and of course, we've got units reported here. So this is looking like a very good answer, one we can safely underline and move on to the next question. Let's try another one. Okay, current. The recommended current for an LED is about 0.02 amps. What's that in milliamps? Okay, again our statement. There's 1,000 milliamps in every amp. So if we want to convert amps to milliamps, we choose the form of this that has milliamps on the top, which is this one right here, 1,000 milliamps per amp. And we can just multiply the number, 0.02 amps, times this figure. 0.02 amps times 1,000 milliamps per amp. Amps cancel out. 0.02 times 1,000 is equal to 20. So our answer is 20 milliamps. And we can ask ourselves, is that number reasonable? Well, we can say we went from amps to milliamps. Milliamps are smaller, therefore this number should get bigger, and it did. We remembered to report our units. Those are the units that were asked for. Looks like a pretty good answer. I think we can underline it. All right, example 3, mega ohms. So we're given a question. There are 3 1.0 mega ohm resistors in series. What's the resistance of the circuit in ohms? Now, of course, you would use the guess process. I'll skip it here to save a little bit of space. So the first part of our question is 1.0 plus 1.0 plus 1.0 mega ohms is equal to 3 mega ohms. So now we've got our answer, but it's in the wrong units. In this case, because they specifically asked for ohms. We might question their judgment because, of course, we say, well, we like it between 1 and 1,000. But, they're looking for ohms, we'll give them ohms. So, there are 1 million ohms in every mega ohm. This term has ohms on the top, which is what we want, because that's the unit we want to get to. We can simply multiply that value times 3 mega ohms. Notice that mega ohms is on the bottom in this part, on the top in this part, so they cancel out. 3 times 1 million. Ohms is the only unit left. So the answer is 3 million ohms. And is that number reasonable? Well, certainly we can say it's a very big number, which we expect. We can also confirm that we haven't changed this value. And also, we can say we reported the units, and these are the units that the teacher asked us for. Okay, so let's summarize. Big day today. We talked about resistors in series and how the current drops and the resistances add together. We talked about how most useful circuits have more than one path for electrons, and the current in these parallel circuits is different for each path depending on the relative resistance. We talked about how electrons will prefer the lowest resistance path, and current will be higher through the path with the lowest resistance. And we talked about the danger of short circuits. When we build a parallel circuit, we need to make sure that every path in the parallel circuit has a load, or we can risk having a short circuit. Okay, that's our day today. Go ahead and work on the worksheet. I think we might leave the activity till tomorrow, but we'll see how much time we've got. Thanks very much. Have a great day.